Welcome to the series on finite analysis of 1D elements. In the previous video, we discussed about matrix analysis of 1D elements and assembly of 1D elements. In this video, we are going to solve one numerical using the concepts which we discussed in the previous video. So let us start. Figure shows two springs having stiffnesses 12 and 8 Newton per millimeter respectively, which are connected in series. One end of the assembly is fixed and a force of 60 Newton is applied at the other end. Using FEM, determine the displacements at nodes 2 and 3 and the deflection of the individual springs as well as the reaction force at the support. So this figure is given. So let us start the solution. We have been given the two spring. So let us consider this as element 1. This is element 2. Okay. So K1, which is stiffness of the spring 1, which is given as 12 Newton per millimeter. K2 is the stiffness of the element 2, which is 8 Newton per mm. And F3 is the force acting at node 3, which is given as 60 Newton. So let us plot a discretization diagram. So let us mark the nodes with node 1, 2, and 3. Okay, U1 represents the displacement at node 1, U2 represents the displacement at node 2, and U3 represents displacement at node 3. R1 is a reaction at node 1, which we have replaced this support and we have marked reaction. And F3 is the force which is given in the problem 60 Newton, which is acting at node 3. Now let us plot the element connectivity table. So for element 1, as we have discussed in the last video, we have global node numbering as well as local node numbering. So here 1, 2, and 3, these are the global node numbers, whereas each individual element, when we consider, it will have the local node 1 and 2. So for element 1, we have local node 1 as 1 and local node number 2 as 2. These are, please remember, are global element numbers, global node numbers. Okay. For element number 2, we have the global node number 2 as local node 1 and global node number 3 as local node number 2. So therefore, total degree of freedom of the system, which we calculate as DOF per node multiplied by total number of nodes. Now, as we are solving one-dimensional problem, the DOF per node will be 1 and total number of nodes we have 3. So therefore, we have 1 into 3 equal to 3. So therefore, the size of or the dimensions of the global stiffness matrix will have 3 by 3. Now let us write the element stiffness matrices. For element 1, we have K1 that is equal to K1 minus K1 minus K1 K1. So let us substitute the values of stiffness for element 1, which is 12. So we'll have element stiffness matrix for element 1 as 12 minus 12 minus 12 and 12. So let us write the node numbers as column numbers 1 and 2, which are associated with the element 1. Similarly, row numbers 1 and 2, which are associated with node 1 and 2. Similarly, for element 2, we have K2 is equal to K2 minus K2 minus K2 K2. Let us substitute the value of K2, which is 8. So we have the element stiffness matrix for element 2 as 8 minus 8 minus 8. Let us write the column numbers and row numbers as node numbers associated with element 2. So we have node numbers associated with element 2 as 2 and 3. So we'll have the numbering as 2 and 3 for columns as well as rows. Let us compute the global stiffness matrix, which is given as K is equal to K1 plus K2, that is summation of elemental stiffness matrices for both the elements. Now we have K1 is equal to 12 minus 12 minus 12, 12. Let us write the global node numbers as column numbers and row numbers. Similarly, we have K2 element stiffness matrix for element 2 as 8 minus 8 minus 8. Global node numbers for elemental stiffness matrix for element 2 are 2 and 3. Now let us write the global stiffness matrix. Now while writing this global stiffness matrix, we have to take care of the correct order of is global node numbers 1, 2, and 3. So let us learn how to write this composite matrix or global stiffness matrix. So for writing element 1 of global stiffness matrix, we have to look for column number 1 and row number 1. So that column number 1 we have in element 1. Okay. So column number 1 and row number 1 gives us the element 12. So first element of global stiffness matrix is 12. Similarly, second element of a global stiffness matrix, we have to look for column number 2 and row number 1. So we have minus 12. So the second element is minus 12. Similarly, to write the third element of global stiffness matrix of row 1, we have to look for column number 3 and row number 1. So we do not have column number 3 we have, but row number 1 we do not have. So the element is 0. Similarly, for the second row, the first element we have to look for column number 1 and row number 2. So that gives us the element minus 12. Okay. So the first element of second row of global stiffness matrix is minus 12. Now to write the second element of second row of global stiffness matrix, what we have to look for? We have to look for column number 2 and row number 2. So column number 2 and row number 2 we have in both the elements, element 1 as well as 2. So what we have? We have in first we have 12, in second we have 8. Okay, so the second element will be 12 plus 8. Now the third element of the second row will be, we have to look for column number 3 and row number 2. So we have minus 8. Okay, so the third element of second row will be minus 8. Similarly, we can write for row number 3. So row number 3 we have to look for the column number 1 and row number 3. So we do not have row number 3. So we have the element 0. Now second element will be what? It will be column number 2 and row number 3. So here you can see, okay, column number 2 and row number 3. We have minus 8. So therefore, the second element of row number 3 of global split matrix will be minus 8. And the final third element of third row will be column number 3 and row number 3. So what we have? 8. So therefore, we have the third element of row 3 as 8. Okay, so I hope you have understood how to write this composite or global stiffness matrix, which plays a very important role in estimation of nodal displacement. So therefore, the final global stiffness matrix will be 12 minus 12, 0, then minus 12, 12 plus 8 is 20, so 20, then minus 8, then 0, minus 8 and 8. Okay, the global node numbers were marked 1, 2, and 3. Okay, now let us write a global displacement and global load vector. Okay, so let us recall this free body diagram of the system. So with the help of this, we can write the global displacement vector as it is nothing but a matrix of global displacements at each node. So for node 1 we have u1, for node 2 we have u2, and for node 3 we have u3. So therefore global displacement matrix will be u1, u2, u3. Similarly, force matrix you can write, it is the matrix of the forces acting at each node. So F1, F2 and F3. So at node 1 you can see here we have reaction R1 which is acting towards left. So as per the sign convention, forces acting towards left are we have considered as negative. So therefore we have F1 as minus R1. At node 2 we do not have any force. So therefore the force at node 2 will be 0. And at node 3 we have force F3 which is acting to the right and has a magnitude of 60 Newton. So therefore we have F3 is equal to 60. Therefore the global load vector F will be minus R1, 0 and 60. Now let us write the global load displacement force relationship. It is also known as the global relationship. So it is written as K into UN, that is equal to F. So let us write the global stiffness matrix which we have 12 minus 12 0, then minus 12 20 minus 8, then 0 minus 8 0 8, and then u1 u2 u3 that is equal to minus r1 0 60. Let us write this as equation number 1. Let us write the global node numbers for column as well as the rows. Okay, so we have considered this as equation number 1. Now let us estimate nodal displacements. So at node 1, since there is a fixed support, the displacement U1 is equal to 0. Okay. Now using Gauss elimination approach, rows and columns from global stiffness matrix and rows from global load and displacement matrix corresponding to node 1 are eliminated. Okay, so from equation 1, we can delete the columns and rows related to node 1 from global stiffness matrix and rows from the global displacement as well as force matrix. Okay, so after elimination, what we have? We have the matrix 20 minus 8 minus 8 multiplied by u2 u3, that will be equal to 0 60. So using this we can write the equations as 20 into u2 minus 8 into u3, that is equal to 0. That is the first equation. And second equation will be minus 8 into u2 plus 8 into u3, that will be equal to 60. So by solving these two equations we get u2 is equal to 5 mm and u3 is equal to 12.5 mm. Now let us compute the deflections of the springs. So deflections, how we calculate? It is nothing but a change in displacement or deformation at that particular node. Okay, so deflection of the spring will be delta 1 is equal to final deformation minus initial deformation, or final deflection minus initial deflection, that is u2 minus u1. So u2 we have 5, u1 we have 0. So therefore deflection of spring 1 will be 5 mm. Similarly, for deflection of spring 2, that is delta 2 will be final deflection minus initial deflection. So U3 minus U2, that is 12.5 minus 5, that is equal to 7.5. Now let us compute the reaction at the support. So from equation 1, this is the equation 1 we had. Okay, so what we can write? 12 into U1 minus 12 into U2 plus 0 into U3. Okay, that is equal to R1. Okay, so we can substitute the values of U1 and U2. So U1 is 0, U2 is 5. So therefore, we have R1 is equal to 60. Now, how to cross check whether our solution is correct or not? We write summation of fx is equal to 0. Okay, so therefore, whatever reaction we get, that must be equal to and opposite to the force which is acting at node 3. So F3 is equal to 60 Newton. Okay, and our reaction value is 60 Newton in opposite direction. So therefore, our solution is correct. Thanks for watching. If you like the video, like, share, and subscribe the channel.